Okay, good evening, everyone, once again. So today we are back with our machine learning class. We had to do a bit of going through the classical machine learning methods last week, and we touched a bit on the decision trees, the random forest, and we went a bit into detail. And then last Monday, we concluded with support vector machines, with k-means clustering, with k nearest neighbors, and we also looked a little bit at the other clustering DB-scan and so on. The one thing that we didn't really touch was PCA, which is for dimensionality reduction. I did promise that we will take a look at that today as part of feature engineering. So we'll see if we can we'll be able to do that. We do have a lot to do today on feature engineering. If not, then we'll continue. We'll touch it again later time. So today we are going to look at feature engineering. And when we say feature engineering, what do we really mean by feature engineering? Um, Essentially, when we have models that we want to train, we typically have so the first thing I think I always tell everyone is to remember that whatever data that you are training your machine learning model on, right? At the end of the day, the model only sees numbers, right? It doesn't matter what shape or form that data comes in as, right? It doesn't really matter whether it is an image, whether it is text, whether it is a scan document, whether it is a sound, speech that comes in as sound, no matter what it is, right? Um, at the end of the day, this information or this data must get to the the um, the machine learning model, whichever one it is. It must get to that model in the form of numbers. That's the bottom line. That's how it must end. And because it needs to get to the model as numbers, I guess one of the tricky questions in machine learning engineering is how is the best way, or what's the best way, what's the best shape or form for us to convert, whatever data or information that is coming in that I want to use to train my model, how do I convert it into numbers? This is a very important question. If we cannot figure out that question, then in a way, we are just saying that we cannot train that model, right? Because if you don't convert it to numbers, then you really cannot bring those numbers or that information to the model in a way that the model will understand it, right? And thereby train on it. So in the past weeks, we have essentially been doing all kinds of things using numbers, right? Linear regression, logistic regression, um, classification. We've done decision trees. We've done all of that. But the common denominator in all of that is that you are training those models using numbers. At the end of the day, that's what you're doing. You're training them with numbers. You're not training them with names. You're not training them with alphabets. You're not training them with pictures, right? When you want to calculate the cost or loss function, you are calculating that with numbers, right? When you want to calculate the gradient, right, you are calculating that with numbers. So the question you need to ask yourself is, okay, if I am using numbers to do all of these things, and I want to train something to recognize an image, right? Or categorize things into male or female. How do I calculate the gradient of the word male, or the word female? Is that even possible, right? Male is language, is a word. a number. So I cannot calculate gradient of that. So I guess the question would be, you know, in order for us to make progress, we have to be able to transform everything that you want to train your model on into numbers. In fact, part of what we did with transformation, I think some of you did that. It was basically um, standardization, right, or normalization. So if a number is too large, we apply some mean and standard deviation to those numbers, and we bring it into within a small range or a smaller range of numbers so that the gradient will not explode and all of that, right? So that's already some kind of feature um, preparation, right? It's a kind of feature preparation. So today we are going to look at the generic principle and process of, preparing the features that you want to train your models on. You need to prepare those features in such a way that you can then convert them into numbers that are within a range that you will use to train your model, and your model will not blow up, you know, because of gradients that are too high or numbers that are too high. So that is a summary of what we are looking at today when we say feature engineering. And today we are going to look at what is feature engineering. We're going to look at what is a feature, right? We're also going to look at why does it even matter? Why do we bother about features, right? Then we are going to look at the various steps of feature engineering. So we'll talk about data cleaning being the very first step. So if you remember when we were talking about the training pipeline or the training process for machine learning models, right? If you remember very well, we actually talked about data preprocessing, right? Data preprocessing, cleaning the data, normalizing, removing empty values and all of that, right? So that's the first step, and we're going to look at that. But that's not the only thing, right? When you are doing, training, when you are preparing data to train a model, it's not just enough to say, okay, let's remove um, null values or let's turn dates into numbers and so on. But at the end of the day, we need to turn all this information into some kind of shape or form that the model you are training, be it a simple linear model or a decision tree or a random forest or SVM or even a neural network, it should be able to just crunch those numbers and then do something with it. So that is what feature engineering is. So we start with data cleaning, then we will talk about feature transformations. So feature transformation allows you basically to transform a feature, right, from a format that is non-numeric, okay, like a text format or whatever, into a feature or that is numeric. That's basically what feature transformation is. So you are basically going to transform from one form to the other. So look at some of the ways to do that. How can you encode categorical variables? So a categorical variable, we'll talk about that. How can you do feature creation and extraction? So this is done in situations where maybe just going with the raw primitive features may be a bit difficult. The model cannot learn. So you create additional features that are a bit more complicated than the raw features by combining those features with other ones, right? And then that helps your model to learn faster. Then we'll talk about text and datetime features, which is very, very key. It's very, very important that we know how to transform text features. Like I said, you cannot calculate the gradient of a word. So you have to convert it to numbers. And then date time. Date time is another very interesting kind of data type, which if you do not know how you transform it, right, your models will not learn properly. Since date itself is chronological, but we human beings, we turn that chronological date and we write it as letters or numbers, right? But those numbers have chronological meaning. So that's very important. Then we'll talk about feature selection. Then we'll talk about the best practices and pipelines. So pipelines, we'll look at that kind of as a hands-on. Pipelines is provided to us by sklearn for us to be able to basically loop in our feature engineering into the training process so that you don't need to always try to remember when you want to train your models. So what is feature engineering? So feature engineering is simply the process of transforming raw data into features that can be used in machine learning models to improve their performance and predictive accuracy, right? So it's that raw data that you have, but that raw data is not in a form that you can easily throw into your machine learning model for it to learn from. So you need to do some kind of transformation, right? Otherwise, you will not have a high performance or good performance of those models. Then we also, it involves selecting, creating, and transforming variables. And these variables are the variables that come from your training data, right? So sometimes it could be, like I said, the variables could be words or sentences or images or bitmaps. It could be um, numbers, whatever it is, right? So you transform these variables, from raw data to make them more suitable for algorithms, right? So it helps the model to better understand and learn from data. That is basically what feature engineering is. It's all of what I said, but this is a way of concisely stating it. So why does feature engineering matter? Like I said, um, models only deal with numbers. That's simply it. But if you are not able to transform these features properly into the equivalent numbers that will represent relationships between those features, then you will not have very good models. So 80% of machine learning success comes from good features. So even simple models that you feel that they don't have capacity to learn a lot, you can actually make them do very well if you do good feature engineering, right? And like they say, models fail when data is bad, not when algorithms are bad. So this is basically saying that in most cases, the algorithms are pretty okay, very good, depending on whichever algorithms you use. They're pretty okay, right? But if you don't do proper feature engineering, then you might even find that your models are failing. Not because you chose a wrong algorithm, but because you didn't do proper feature engineering. So that's why feature engineering is very important, right? In fact, if you were to take a linear model, right, you can actually train it to predict a polynomial function just by doing a polynomial feature um, creation. That is, you take some of the features, and you actually create a new feature that is a polynomial combination of the independent variables. And use that to train a model. You'll be surprised that a linear model could become really good at predicting that. Maybe not perfect, but really good. Much better than if you did not do any feature engineering. So that's just to show you how powerful feature engineering is. So what are the aspects of feature engineering? Like I've said, you have selection where you first of all choose which of the raw data points that you want to engineer and how best to engineer it, right? So it is not all the data points in your data set, right? Or rather, let me rephrase this. It's not all the features in your data set. All the data points matter because the data points basically form the sample that you will use to train your model. But for each data point, there are features, right? So think of them as the X1, X2, X3, X4s, the independent variables. right? That combine in some way, to influence the outputs or the prediction, right? It is not all of them, right, that will be useful for you, for your model. So sometimes people have this idea that, okay, if I have a data set and I have 1,000 features, I should just throw all 1,000 features into the model. That is not correct. There are some features that have no impact or correlation with the prediction or what's going on. So in that situation, you could basically just omit those ones. Then there are some features that are basically um, a duplication in terms of correlation with the output, right? That you are predicting, right? Or the value that you are predicting. You may have two or three duplicate values that basically have the same correlation. And the reason why they have the same correlation or effect on the outcome is because both of them are related. There is some kind of relationship between them. So that may be a redundancy. Okay. So you have to have the ability to choose and decide which of the variables that you are going to use, in training your model. That's the first step. So selection of which features I want to use to train. But in most cases, right, you would always want to pick as many features as possible. In fact, pick all features that matter, right? But again, you still have to apply that critical thinking to decide which one you should do. Then the second thing is creation. You can then create new features, like I said, from the existing ones. So for example, if you were asked to predict something and you found out that maybe you are given a linear model, right? And you found out that that relationship is polynomial. You could create a new feature that is a polynomial combination of some of the raw features. That will help the model to do a better job of predicting. Okay, so creation is when you create or generate new features from existing ones using transformations. So a good example is if you are trying to predict cost of a house, and one of the features that's given to you is the age of the house or the year that the house was built. Now you ask yourself, what really matters, in predicting? Is it the year that the house was built or the age of the house, right? So it's probably the age of the house that matters more than the year it was built. So you will create a new feature called age, right? By calculating the age from the day of completion or date of completion of that house. So that's a good example of creation. So you always look for opportunities to, okay, can I transform this feature into another shape or form that has a higher um, impact or relevance, okay, to what I'm trying to predict. That is creation. After you finish creation, then the next thing you will do is transformation. So transformation is converting the data that comes in, the raw data, into a more suitable format, right? So when we say more suitable format, at the end of the day, it has to become numeric, simple, right? So some of the things you can do to convert the data will be encoding. So encoding is one way. So encoding is when you turn non-numeric data like text or categorical labels into numerical representations. You have to come up with the numerical representations of features. Otherwise, you can't do anything with it, right? So that's encoding. So encoding works for any raw data or raw feature that is not numeric, right? Then scaling is normalization or standardization of numerical features to ensure that they are on a similar scale, right? Which prevents some features from dominating others. So scaling up applies to numerical features. So I think we've done some of you in your submissions. I saw you do that, you know, normalizing or standardizing. So if the scale is too large, for some features, if the scale is much larger than others, then you have a situation where the one that has larger, values will dominate the one that has smaller values and will dominate in the gradient, right? The gradients from those ones will become bigger and it will affect the parameters and basically how you train. The parameters of those ones with larger scale would tend to be too small, right? So you normalize, okay? Normalization is when you kind of what we call scale and center, right? Um, sorry, scale. The standardization is scale and center. So we'll talk about some of those. Um, so the benefits of the feature engineering is one, by providing more meaningful inputs. Feature engineering helps models to learn complex patterns more effectively, right? And to reduce noise and irrelevant information, because you do that by simply removing the features that don't matter, but you also do it by the normalization and standardization, right? It helps the model to make more accurate predictions, and it helps the model to simplify interpretation by creating more informative features, like I said earlier. So those are the benefits of feature engineering. So we now move on. What is a feature? A feature is any measurable attribute or variable that you use to train your machine learning model. And that is what the model will use to make predictions. In other words, a feature is an aspect of the data that influences the outcome of your prediction or what you want to predict. So a good example is if we go with the example of um, price of housing, right? So a feature would be the size of the house, the location of the house, the year it was built or the age, like we are saying now, the rate of deterioration, right? Maybe the what else? The I think I've talked about the key ones. So those are the things that will say, okay, any of these things or all of them combined in different ways would affect the cost or pricing of the house. So each of those things is a feature. And if we now want to map it to what we're talking about when we're discussing linear regression and all of that, each of those things can be considered an independent variable because the price of a house, well, it depends on other things, but with respect, sorry, the age of a house depends on when it was built. So in a way, it's dependent on something else. But in the context of um, determining the price of the house, it is the independent variable. So it's one of them. So you can say that X1. Okay. Then what else? The size of the house. That's another variable. Okay. Another feature, basically. Then what else? The location of the house. If it's located in a big city, it's likely going to cost more than if it's located in a small town. Okay. And other things. So each of those form features. So what are the types of features that we can have? So like we've already mentioned, we have several broad categories of features. So we have the numerical features. Numerical features are features that are represented as numbers. So age, um, height, cost, all of those, even um, price, you know, year of birth, all of those are numerical features because they are numbers. Okay. So, and for numerical features, we have two types. We have what we call continuous and then what we call discrete, right? Continuous are numerical features where the value can be anything. It's a continuum, right? So age is a good example. Income, height. I've always said age is not a discrete value. When somebody says you are 5 years old, you're not really 5 years old, right? You could take 10, three different 5 year olds, and you find that one of them is 5 years and 3 months and 2 days and 5 seconds or 5 hours. The other one will be 5 years and 6 months and 2 days. So we are the ones that kind of, chop off um, you know, the smaller, part of it just to make it easy. Oh, okay, this person is 5 years. But the age is actually a continuous number, right? So that's a good example. Another example is income. Income can be any number. It can be 1,000, 1,200, 1,233. It can be 1,250. It can be 10,000. It's a number. It's continuous. Height, the same thing. People don't jump in height. The height starts from whatever, 5'6" or 1.85 meters, 1.75 meters, 1.74, 1.73. It's continuous, right? But we also have what we call discrete. Discrete is something that's what we call integer or whole number. So you cannot have, like, number of children is a good example. You cannot have half of a child or half a child, right? So when you are saying number of children, it's always going to be discrete. So one, two, three. There's no number of children in between one and two. It's either one or two, right? You cannot say I have one and a half children, even though some people consider maybe babies as half children, but they're still a full, child. So that's a discrete numerical feature. Then we talk about categorical feature. So a categorical feature is a feature that you use to basically categorize. So because it's categories, there are only a limited number of categories, right? Or items or classes in that category, right? So categories are like a set. And in that set, you have discrete possible values that are limited. That's categorical. So you have two types of categorical. You have the nominal categorical and you have the ordinal categorical. The nominal categorical is the one that is kind of um is based on, it's just name. There is no sequence to it, right? There is no sequence. You cannot say one is greater than the other, right? They are, I don't know how to call it. There's no numerical or sequential um, connotation or denotation to a nominal category. So a good example is your gender, male or female. There's no one that you say, okay, this is greater than the other one, even though some people may not agree to that. Same thing with countries, inherently you cannot say this country is, you cannot do an ordering of countries, except maybe you're using alphabetical order or something, right? So that's a nominal, it's just it's just categories, right? And like I said, a category has a limited number in each number of classes in each category. So for example, gender, you have a limited set. So you can say male, female. Well, there are other ones now that people are talking about, which I don't really know about. But countries, you can count the number of countries in the world, maybe 193 or 195 or so, right? And that's all. There's no country in between two countries. So those are categorical, nominal. Then ordinal are categorical features that there is some kind of order. That's why it's called ordinal, or sequence, right, between them. So, for example, educational level, you can say primary, secondary, university. So, inherently, there is an order or a sequence to them. Then we also have date time features. So, date time just stands on its own. And there are two ways we can look at date or time. In programming, in machine learning, generally, date time is considered as a single thing, a continuum, right? Like I said, it's chronological. It starts somewhere and it continues, and it continues, never ends. Like that's time. But an instant in time is what we call a timestamp, right? And that timestamp has a value. In the context of programming, we measure time based on a reference start point, a reference starting point, in time. And that reference starting point will normally give you a reference value, maybe like zero or whatever. So in those days, like 1st of January 1970 was a reference starting point in time, and we give it a value of zero. And then from that point, we count the seconds from that time to now, and that is what we call timestamp. Others count in milliseconds, right? And so on. So that is a timestamp. Then a month, we know what a month is. A month is basically, well, it's one of the ways to measure cycles in time, right? Day of week, same thing. So those ones don't need explanation, but those are date time features, and um, they're still um, well, all of those still come under timestamp, right? Because they're basically a measure of where we currently are in time. Then the second one is what we call time since last event. So this is a kind of time interval thing, time since. Time since is a time interval. So if you say 2 weeks ago, that 2 weeks ago is not an absolute measure of time, but rather it's a relative measure of how much time has passed between two events, between a time in the past and now, or some other time in the present, past, or future, right? So time since is also a date time. Interestingly, so the age, your age is actually a kind of time since, right? Even though you don't think of it that way, because your age is basically the number of years that have passed since the day you were born. So it's a kind of time since. The only thing is that we have normalized it to the year, right? Rather than using a timestamp or something. Then we have text features. So text features are basically text, anything that is text, right? Reviews, comments, descriptions, prompts, whatever. Those are text features. And then we have what we call derived features. So a derived feature is a feature that you derive, as the name implies, from other features. So a good example is when you're calculating ratio. So you are taking ratio of two features. That's a ratio. Divide one feature by another. A good example is debt to income. Another example is balance, or another example is profit. So if you had a feature called cost price and another feature called sales price, then the profit is a it's not really a ratio, it's a difference, but it is a derived feature as well. Then we have aggregation. Aggregation is when you combine values from multiple data points, right? The same feature from multiple data points. So for example, a sum is an aggregation. So when you say sum of, that's an aggregation. Mean is also another aggregation, right? Um, and there are other examples like that. So basically all the measures of statistical, um, what do you call it? Um, the statistical measures, right? They are all kind of aggregations. So those are the broad types or categories of features. So we now move on to what do we do, right? When we want to engineer the feature engineering. It starts with data cleaning, like I had said. So data cleaning is the first step. And why do you have to start with data cleaning? Because your data needs to be consistent, it needs to be complete, and it needs to be accurate. It needs to be free from duplicates or obvious errors. Otherwise, you are training your machine learning model on nonsense, garbage, basically. And if you do that, you cannot expect your model to give you good results. So, like they say, garbage in, garbage out. That's basically what's going on. And we already see that 80% of machine learning success comes from good features. Models fail when data is bad. So you have a higher probability that your model will fail from bad data than it will fail from a bad algorithm. In most cases, in fact, people these days they say there's no such thing as a bad algorithm. There's just bad data. But that's not strictly true because there are situations where you can pick an algorithm or a model architecture that is insufficient for the extent of data or complexity of of interactions, right, within those data. So that's it. But it is a good thing to know. Now, these are the reasons why we do data cleaning. Then, what are the things that you do? So we look at some of them. The first one is handling missing values. So this is a decision you need to make, and it's part of your feature engineering. You need to sit down and think and ask yourself, okay, what should I do for missing values, right? And there are multiple options here. These are not all of them. It's not an exhaustive list, but you could say, okay, for data points or rows that I have some missing values, maybe like I'm trying to model housing pricing, and some of the data points don't have the date that the house was built. So what do I do? Right? So one of the things could be, let's just remove that one. I don't want to give myself headache, right? So just remove that row. But the danger of removing rows is that if your data set is small, you begin to lose context. So it's something for you to think about. Should I remove the rows that don't have sufficient data? And what if most of the rows don't have sufficient data, especially on some columns, right? You could have some columns that are like 80, 70, 80% of data is missing. And if you remove the whole row because of those columns, what happens? You lose 80% of your data set, right? So in that situation, you may decide, okay, let me forget about that column. The column itself is the feature, right? So let me forget about that feature. If I'm missing 80% of this feature, it's useless to me, as far as using it as a predictor or as an independent variable that will affect my prediction. So even though that may be a very key feature, but then you don't have the data. So you have to choose either not to train the model or to train the model without it. So the other thing is you could also decide, I want to fill those missing data whether the whole column or some of the whole row or some of the data points. Let me fill it with something. And you have to decide what you want to fill it with. Do you want to fill it with the mean of other features from other data points of the same feature but other data points? Do I want to fill it with the mean, or do I want to fill it with median or the mode? In some situation, it makes sense. This is actually a domain specific decision. You actually need to understand what it means. So if you're a data analyst or a machine learning engineer, I don't understand the significance of it. If you go do this, it may be a wrong thing to do. So this is where domain specific knowledge comes in. So a good example is if I'm trying to do some kind of prediction and it is tied to the age of students in a class, right? Then there are some students that have missing age. Their age is not specified. You could say, okay, it makes sense for me to take the mean age of all the students. This is typically the age of students in this class. I'm not going to be too wrong if I use the mean or the median as the age for some of these students, right? It makes sense. Okay. Oh, we can do that, right? So if you have sufficient domain knowledge, if you're a teacher or someone that works with schools, and that is domain knowledge that helps you to be able to make that decision. So deciding to feel or not to feel actually requires you to have a bit of domain knowledge. This is the main thing I want to point here. Okay. So the third thing you could also decide is look for a simple model, right, that can guess those values, right? A simpler model. So you come up with some kind of model, and it may not necessarily be a machine learning model, right? It could also be a model that uses some kind of heuristic or algorithm to come up with a value. And you say, okay, let me use that to feel it. Then the last one is domain rules. So like I said, in a lot of cases, these are domain specific stuff. So using domain rules, there may be some rules of this is how you can fill in the gap, all right, in this data if you do not have it. Okay, so we'll go with domain rules. So this is the first step for data for feature engineering. You start with data cleaning. So the other things you will do with data cleaning is number two, fix inconsistencies, right? So fixing inconsistencies means things like the typing, okay? Is this supposed to be a number? If it's a number, did they type it in as a string? Was it stored as a string? So if it is a number, you can then do type coercion, what we call type coercion, basically to make this type, which is 45, stored as a string into an int. Then the second thing that you can also do to fix inconsistency, if this is a numeric field that represents an amount and it is formatted as a string like this with the currency and the separator and all of that, you could say, okay, let's clean it up as well and make this into an actual number because it's a numeric field. And one of the things that you need to understand with this is, again, it requires you to have that knowledge. And in most cases, you will have to write um, custom code to do it. There's no library that will do this for you because the library doesn't know the nature of your data, but the library will give the tools to do all of this type data type coercion. Okay, so you can do a coercion that coerces the um, number that is in a currency format into an actual numeric value. Then inconsistent labels. So this happens a lot if you did not constrain, especially if you are collecting data from a survey. So think of like you do a Google form or some other kind of survey monkey or some other kind of survey to collect data. And you have a field that says, okay, type in your gender. But because you say type in your gender, it did not say pick your gender from this list, which is a better way of collecting the data. And that's one of the things that people learn. This helps in data collection. When you're collecting data, you always have to kind of constrain the users where you have categorical data. It's always better to give them a list of all the possible choices. Let them pick from it, a drop-down box or check boxes or radio buttons in the form. Okay, rather than asking them to just type it free form. You don't ask people to type categorical data. because they will type different things. Some will use uppercase M, some will use lowercase m. Some can just use a single letter, like in this case of gender, you say type your gender. Some can even just mistype it, wrong spelling and all kind of stuff. So when this happens, right? Yes, there are times when you get data that looks like this. You still have to write your code to be able, you have to write custom code that will normalize these inconsistent labels into the one that you decide or you choose it to be, right? So sometimes it may require, okay, changing everything to lowercase and, maybe taking only the first letter. Or if I want to go with this all lower male, for example, I would then look for anything that has M as the first this thing and convert that one to male. But somebody could write man, man, for example. So how would you you convert man to male, right? Another person could write woman, and that should map to female. So you now see that you are actually going to write some kind of rule-based logic that will say, okay, if it is woman, then change it to female. If it is a girl, change it to female. If it is, you see that kind of thing. So this kind of inconsistent label is a very big headache in particular for your data cleaning, pipeline at that phase, at that point. So you have to write a lot of rule-based. Even sometimes you find that some data will still miss and pass through the filter because maybe you say, okay, if it is woman. Meanwhile, when you wrote woman, you spelled it as WMAN, right? But the person that typed their own, maybe they don't know how to spell it very well, and they could type WOMEN or WAMON or something, right? Or some could just be typographical error. So how do you handle all of those kind of slight variations here and there? That is a very key aspect. Then the other thing you would do after fixing all the inconsistencies, so you now have uniform values for each feature, you have uniform values or uniform types or uniform categories for each feature. The next thing is remove duplicates. So a duplicate is basically two records or two rows that have the same value all through across all of the features, right? So if you have exactly the same first name, surname, gender, age, date of birth, location, all of that, you can be safe to consider that is a duplicate row or duplicate data points, and you can remove it. So that's the other thing. Then what we call outlier handling. So outliers are basically data that are far from the general cluster of all the data. Like they are just, that's why I call them outliers. They're just out there, right? And most of the time, outliers tend to skew your model, right? And your model kind of tries to adjust to those outliers, and as a result, may not do a very good job of prediction. So in most cases, you don't really want outliers. The other thing is outliers may actually be an indication of an anomaly or an indication of error in the data. So it's something to know about. And there are methods for doing that. We have what we call winsorization, capping, and log transform. So these are all different ways that you can use to clean up the outliers. So after doing that, then the next thing is feature transformation, right? Feature transformation. So with feature transformation, what you're doing basically is that you want to transform your features so that your model will have better performance. So what do we mean by transformation? Remember, transformation is where we are taking those values and we have to make them into numbers effectively, right? So the different steps in feature transformation, you start first of all with normalization. And well, before we go into that, so the 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 value of feature normalization or feature transformation, apart from normalizing the ranges so that all the features will be kind of within the same range, like we said. So I don't have one feature overbearing or kind of you know um affecting too much the outcome of your training. You also have what we call skewness, which you can use feature transformation to reduce the skew. Then you can improve numerical stability. So when we say numerical stability, For some of you, if you remember when we did the linear regression of multiple variables, you remember that you started training and you saw that your gradients were exploding, right? Your gradients were increasing, the cost was increasing, everything was increasing, right? Basically increasing to the upper limits of the numerical range that the computer allows, right? On the other hand, we never saw the opposite case where it decreases to the lower limit, right? In both cases, is what we call overflow. And you typically don't want that overflow. Overflow happens when your numbers are too large. So either the range of the features, right, is too large or too small. So if you scale or transform or normalize, you end up having more stability because your numbers are within a kind of a small range and you will not likely have the exploding kind of gradient that we saw. Then the other value of having transformational features is that it allows your patterns to be more linear, right? And then the last thing is it helps to prepare data because there are some algorithms that assume that your data is coming from a normal distribution. So a normal distribution for those who did a bit of mathematics is a distribution that comes from a bell curve where the highest percentage of data points tend to be in the median, right? What we call normal, where most of the features match, and then you also have what we call extremities, where the probability of this data being in the extremities is lower and lower. So it's a normal curve. That's a normal distribution. Okay, so what are the steps to feature transformation? So the first one is scaling, right? Scaling, like we talked about, can be either standardization or normalization. So we have two types of scaling. The standardization, or alternatively is called Z-score scaling, is where you center the data around a mean of 0 and a standard deviation of 1, right? And these are good for linear models. We use that for our linear models when we did a linear regression. And it's also good for logistic regression. It's also good for neural networks, right? So when we talk of neural networks, when we get into that, you'll find that you always have to do, there's a lot of normalization in neural networks. There's what we call batch normalization, there's layer normalization, there's all kinds of normalization. And basically that's a mean of 0 and standard deviation of 1. Then the support vector machines, we also saw that you need to do some kind of scaling or normalization. Then we have the min max normalization. So in this one, you are scaling the values to a range of 0 to 1, right? So in this case, the lowest value is going to be 0 and the highest value is going to be 1, right? That's min max. It's not centered around 0, right? Standardization means it's centered around 0. So the median or the mean value will be at 0. And with a standard deviation of 1, that means other values can extend outwards from 0 in the positive direction, right? Between 0 to 1, and also in a negative direction from 0 to -1. And it could go all the way beyond that. But even though the range may extend to 1 or beyond 1, but the standard deviation of all your data samples is going to be 1. That is standardization, right? While min max is the lowest value is going to be 0, and the highest value is going to be 1. So what you do in that case is basically you are just taking each value, you subtract its value from the mean, and that difference you divide it by the range. The range is the difference between the lowest and the highest, which is the mean and the max. So we are going to look at how we do that a bit. So then we have log, square root, and box-Cox transformation. So these are other ways of transforming. So you use logarithms, right? And it's typically used to handle skewed data. So data that the if you see that the data is too large or too skewed or the range is too high, right? You can use a logarithmic transform. And the logarithmic transform is basically going to give you not a scale of 0 to 1, but rather a scale um, where it increases by orders of magnitude of 10 or 2, right? So that's how it goes up. So that's also another way. Then we have binning and bucketing. So binning and bucketing is a way of converting a continuous numeric feature or value into categorical. So I've mentioned this before. So a good example is ages. So you have age. Age is a continuous number, but we can decide to create age groups and we bucket the ages into these age groups. So for example, you could say, like I mentioned it some time ago, you could have, babies, you could have toddlers, you could have children, you could have teenagers, you could have young adults, you could have adults, you could have seniors, right? So those are now age groups. Or you could also represent those age groups with numbers, right? So you just create bins. So this is another way that you can transform if you don't want to have to deal with continuous data. In other words, if I don't want to do linear regression, I don't want to do a regression problem. I want to do a classification problem. Sometimes you can decide to bin the inputs because if you use the input as is, it will make it really difficult for you to do regression. So there are situations like that. So another example is salary bands, right? Salary is a continuous numeric feature, right? It can be anything, but you could also decide to create bands and put bucket people based on the salary bands. Another example is risk levels, right? So these are all examples of um, binning or bucketing as a means of feature transformation. Then after that, the next thing is what we call encoding, right? Feature encoding. You typically do encoding for categorical features. So remember, a categorical feature is a feature where you can have only one of any set of values, right? But in that one of any set of values, right, for us to convert that into numeric values, we will still have to um, create numbers that match it, right? So um most models, like I said, cannot work directly with text categories because you have to deal with numbers. So there are different ways that we can encode categorical features. By the way, let me even back up and tell you that by the time you do binning, right? Binning converts your continuous value into categories. So it becomes a categorical value. So after binning, you still need to do the encoding of the categorical values. So you see that difference, right? Versus if I was just using the continuous numerical values, I probably don't need to do any encoding. I probably just only need to do standardization or a min-max normalization or a log transformation. But when I bin numerical values into categorical, I then need to encode the resulting categorical values, okay, to form the features. So what are the methods of encoding categorical features? There's what we call one-hot encoding. So a one-hot encoding is an encoding whereby you give every other member of that class or category zeros, but the one that's the feature has, you give a value of 1. So you are essentially creating a vector, and when you create that vector, then when you have a value of, so for example, let me just give an example. You could have let's say you have 3 categories, right? Red, white, blue. Red, white, blue. Those are 3 categories. For each of those, each of the classes in the categories, there are 3 classes in that category. Red is one class, white is the second class, blue is the third class. So you have 3 classes in that category. And for each of those classes, you will have a an element in the vector. So you're going to have a 3-dimensional vector. A vector has 3 elements. 0, 0, 0. There'll be the 3, right? The first one would represent the red. The second one will represent the white. And the third one will represent the blue. So a one-hot encoding would mean if the category that I chose for that particular feature, that particular data point, if the category is blue, then it will be 001 because the third position means blue. That's it's a positional kind of encoding, right? So we'll talk more about one hot encoding. So that's just one way of encoding categorical. So this is the code that we use to do that. In sklearn, there is a simple thing class called a one hot encoder that does that. I'm going to go into the code examples later on. I will try to explain one hot encoding first before so that we understand it. Then the second one is what we call label encoding. So with label encoding, you basically just assign IDs, integer IDs, right, to each category, each class in the category. The only problem we have with this is that it will introduce some kind of false ordinal relationship, right? The model may begin to think that there is an ordinality between these classes. So if you give ID of one to one and two to another and three to another, it may begin to learn that order and feel that the first class is greater than or less than the second one, and the second one is less than the third, when actually there is no ordinal relationship. So you have to be careful that if you're using label encoding, use it only for ordinal categories. So for example, if you did a bucketing of age groups and you had, baby, child, teen, adult, middle age, senior, right? Then you can use label encoding, right? Where baby would be zero and, adult and child will be one and teen will be two, adult will be three, middle age will be four, senior, because those have inherent um, ordinal relationship. So that is the thing you need to be careful with label encoding. You can really only use it in that case. If you use it for something like gender, then you may be in a situation where, okay, the model may actually think that depending on which one you give zero or one, it would think that one is greater than the other or something. So label encoding is suitable for tree-based models, random forest, XGBoost for it's also good as a target variable in classification, right? But one hot is really good for when categories are nominal, okay? I didn't mention that. So use one hot when the categories are nominal, so there's no relationship between the categories, and there are fewer than 50 unique categories. If it's more than 50, then your vectors become really big and you start having issues, right? But I think there's some kind of, you know, discussions around which is which. Okay. So all right. So the third type of encoding is the frequency or count encoding. So in the frequency or count encoding, you are basically just replacing the category with their frequency. So a good example is you can represent the city if the category was cities that people live in, right? That is still categorical. You can then replace it with a value count. The only challenge with this is that you may have situation where um, two different categories that have the same count, maybe interpreted as if it's the same category. So again, it depends on the application. Then we have what we call target encoding, right? So target encoding, which is kind of a more advanced, is that it replaces uh, the category with the mean of the target values, right? And it's useful for high cardinality categorical features. It risks leakage, right? It risks leakage. That is, the one thing to take home from that. Then, after that, that is transformation, feature transformation. So the next thing we will talk about is feature creation. So feature creation is where you can create new features based on existing ones, right? Because you want to improve the signal. So sometimes you can add, like I said, ratios, differences, multiplications. You can, change order of magnitude. You can change, the order of the feature. So for example, first order to second order, those are all different things. I've actually seen situations where in feature engineering, you have, in those days, it used to be a common thing. Like if you have x, y, then you now have x squared, y squared, sorry, x1, x2, right? As the raw base features. Then I could have x1 squared and x2 squared. I add the square in case there is a polynomial relationship, right? So the model can learn that as well. So there are several kinds of things you can do, when you're doing feature creation. The first one is the mathematical transformation, which is like what I just talked about. Ratio is one, where you can just do division of two of the features to form a new feature, right? That is a ratio. You can do a difference as well, where you can subtract one from the other. Like I say, closing balance and opening balance, or um, profit minus income minus expenditure and all of that. Multiplication as well. So this is basically just code sample. It's just simple, mathematical calculations. Then the second one is polynomial features. So like I mentioned, you typically use the polynomial features to capture nonlinear relationships. So if, for example, you want to do linear models, or you want to use linear models, but you find that your features have polynomial relationships, then you can create polynomial features. So this is a good example where we use these polynomial features, um, this class in sklearn to create a second degree order 2 of every feature that is already there. So what will happen is that when you do poly.fit transform df salary, it basically is going to create a new feature called salary squared, because you are essentially taking salary and you create a second order polynomial. So every salary in that is going to square it. So you now have a new feature that is kind of proportional or related, to the square of the salary. Now the question you may ask is, if I'm squaring salary, is the number not going to become very big? Because salary is already big, maybe four 10 raised to the power 4 kind of thing, and then you square it. So that's something to take note of. But the sklearn is going to do the necessary normalization as well as standardization, so that you don't have any blow up of your gradients and so on. So the third kind of feature creation is what we call interaction feature, right? So you can actually create interaction features by combining two different features, or two maybe even unrelated features, right? Just to get a better signal. So this is a good example where you create a new feature called income age interaction by multiplying the income by the age. So that's another example of how you can create. Then there's what we call aggregation features. So aggregation features are features that you create by using aggregation functions. So these are normally useful in transactional or time series data. So time series data that keeps streaming in. You can do the mean, which is average. You can do the median. You can do the mode. You can do the sum. You can do the count, and so many other different kind of aggregate functions. So remember, an aggregate function is a function that aggregates multiple values in a data set for that particular feature and calculates an aggregate of it. That aggregate could be either, like I said, the sum, the mean, the max, count, median, and so on. So you can use this to create a new feature that represents those ones. And then we have what we call rolling window. So you can actually calculate rolling window features. A rolling window feature is typically an aggregate based on a narrow or wide window that is related to the current data set. And it's also, again, very useful for time series kind of data and other kinds of data. So a good example is you can calculate a 7-day mean, right? All of these pandas allow you to do this. So you see data frame. So you can calculate a rolling window. This is a rolling window. The window is 7 days, and I'm calculating the mean values of the sales. So you are going to get a new feature that is made up of the mean for the last 7 days. The next day will also be mean for the last 7 days, and so on, right? Of course, for the first 6 days, when it's not up to 7, you can decide to either make it empty or use zeros or something. Then you also do the same thing. You can also calculate standard deviation over the last 7 days. So this is a good example of rolling window features. And these are used for demand forecasting and for anomaly detection, because anomaly detection, you will detect if you use a mean or standard deviation, you will definitely see. So mean actually gives you mean flattens fluctuations, while standard deviation will bring out a single fluctuation. That's the interesting thing. If you actually plot graphs, you'll see those things. So you can use standard deviation, for example, to detect anomalies, right? It is basically going to immediately detect something that has changed, that the change is very big. Then, of course, we talked about binning already. So binning is another way that you can create. So you can take a continuous um, numerical feature and create a new feature by binning that continuous numerical feature. Okay, so the next thing is you can turn numeric text, right? Sorry, you can turn text into numeric features, right? Into numeric representations. So text is very rich, right? And um, it has a lot of different things you can do to it, right? So you can just take the text and you convert text into numerical vectors. But for you to do that, you need to first of all um, clean it and pre-process it. So some of the things you can do there would be lowercase, values of the text. Then you can have removing punctuation like commas, you know, um, removing stop words, um, removing, um, you know, duplicate words. Then what we call lemmatization or lemma and stemming. So what this means basically is that lemmatization is when you remove all of the, what do I call it now? Decorative things around words and you leave behind just a stem word. That helps better understand what it is. Of course, this used to be very nice approaches in those days, right? But these days you can use word embeddings just to do all of that, right? Which is what we we are doing in the other course. But for example, a word like coming, right? You can just lematize it and you end up with come, right? So whether the person says or a word like going, right? You end up with go. So a word like going or gone or went, all of it, you just have go, right? So that makes it easier to just when you eventually encode the the text, they all kind of end up meaning the same thing or representing the same thing. Then we have what we call bag of words. So bag of words is a way of counting how many of each word is the occurrence or frequency of um the words. Okay. So that's very effective, with a small vocabulary. You can just use that to classify words based on the number of occurrence of those words. That's what bag of words does, right? And we have that in sklearn as well. So they call it a count vectorizer. So it basically counts the number of times particular words, occur, for a given feature. Okay. Um, the other things you can do with text, you have reduction of weight of common words. You know, um, you also you have what we call TF-IDF, which is term frequency or inverse document frequency, right? So this is a way of trying to kind of equalize the occurrence of words, right? By reducing the weights of words that are very common, right? And highlighting rare and meaningful words. So you may have in sentences, for example, you may have words that always occur, but they don't really carry a lot of meaning, right? For example, in, of, and, you know, um, and so on, the, those kind of words. So you would typically reduce the words, the weight of those words, right? While the actual words that carry meaning, okay, you would say, okay, let's increase the weighting of those ones. And most words will carry meaning, so you want to increase the weight of those ones. So that's what TF and IDF does. And sklearn also has a class that handles that. It's called a TF IDF vectorizer, right? So it's going to create a vector, and it's going to give the words that are very common lower weights, and meaningful, rare but meaningful words to give them higher weights. Okay, then we have ngram. Ngram is basically a way of capturing sequences of words, right? And you can also use the TF-IDF vectorizer to do that by specifying the ngram range. Then, like I said, there's also embeddings, right? And that's what we use mostly these days in order to make meaning of words. These other approaches were ways that we're doing it in the past. But yeah, you have these three very key embedding libraries or tools. Word2Vec. Word2Vec has been around for a long time and has been used even in before we had neural networks that now do embeddings, or large language models that now do embeddings. Word2Vec was doing a great job of giving very good embeddings for words. And as a machine learning engineer, most of the time you may actually start with a Word2Vec if you want to train a model, because you don't want to um you want to train a model maybe like based on the bias of another model, right? So you could use Word2Vec. Glove is another very good embedding library that also gives you embeddings. So what is an embedding, by the way? An embedding is essentially a representation of meaning of words. So irrespective of what the word is, right, or the sequence of word is, right, it gives you a vector. That's why it's called Word2Vec, right? It gives you a vector, which is a list of numbers that the the numbers in that vector have some kind of significance or meaning with respect to the word. And if you bring words that are similar, you will have vectors that are similar or close to each other. Even if that is words that are similar, not in terms of the spelling or something, but in terms of the meaning. Embedding is basically a representation of meaning, right? So words that have similar meaning will have similar embeddings, even if they are vastly different. So a word like man and guy may have similar embeddings, right? But man and woman will have totally different embedding, because even though man and woman are similar in terms of spelling, but in terms of meaning, they are vastly different. So that's what embeddings do. So we also have the BERT embeddings. So these were like some of the top ones that do that, right? So what comes out of the word embedding is what we call a vector or semantic vector, right? So the semantic vector, a vector, like I say, is a list that contains numbers, or a numpy array that contains floating point numbers, and those numbers have meaning. So after that, then we have what we call feature selection. Some of the techniques for selecting features include the you want to look at um the 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 uh your objective, right? What you want to achieve, right? So the features you select may depend on what you want to achieve. And some of the things that you will look at is you want to improve the model performance, you want to improve the training speed, you want to improve interpretability, and you want to improve generalization. So in that situation, you choose a method based on that. So some of the methods that we use, we have the filter method, right? So then we have the simplest and fastest methods are the filter methods. These don't use any model, right? So a good example is the variance threshold, right? So if you have features that the variation between the values of those features from one data point to the other is very small, you will not, you will eliminate that feature because there's too little variation, right? So it will not really contribute much to what you're trying to predict. Then we have correlation analysis. So in sklearn, you specify a variance threshold. So variance calculates like what's the variance between the features in the entire data set, right? And you can specify a threshold. If the threshold, if the variance of that feature, the values in that feature don't exceed this threshold, then that feature can be dropped, right? So that's variance threshold. Then we have correlation analysis, where you are comparing the correlation or collinearity, right, between the values in the feature, right, or between multiple features. And what you can do then is if you find features that are highly correlated, then you can decide to remove one, all of them, and leave behind just one, because the collinearity basically does not add any value, to what you are training. Then we have what we call wrapper method. So wrapper method is where you use a model to evaluate the subset of the features, right? And with that, you can recursively eliminate, those features. So we have one of the wrapper methods that we have is a recursive feature elimination, right? So you bring recursive feature elimination. This is an example where you're using recursive feature elimination, and then you are using logistic regression. And then you basically do an RFE and you run the logistic regression, right? So you're using logistic regression as a way of running the elimination, right? And then you specify the feature that you want to select. So it's basically going to try to fit the X values, right, into the Y values, and it will recursively remove features where the correlation is very low between the feature and the um the uh the the true value or the label value, right? That's what you do with RFE. It's kind of recursive. And then we have embedded methods, right? So in embedded methods, you basically allow the model itself to determine which features matter. So we have regularization as a very good example of this, right? So we have what we call lasso regularization, which is the L1 regularization. So what regularization does is features that don't matter get a weight that is very low, very close to zero. So effectively eliminating that feature. So lasso is a good example. Then we also have a tree-based feature importance. So this is kind of using a random forest, right, to train or fit on your data, and then it will pick out the features that don't really matter, right? Or it will give you what we call importances, which is um, kind of a list of importance, how important each of the features is, to the label, the Y value, right? And from there, you can then decide which ones you want to eliminate and which ones you want to leave behind. So that's a lot, right? I actually skipped one piece, which is how you can also transform date, because date is a very, very key aspect of the data. So there are many ways you can transform or translate dates, right? So maybe because we're out of time, I'm going to run through dates when we come in next week, right? So and then I'll do hands-on, right? So that we can at least learn how to apply. First of all, do this normally, right? And then use sklearn, because I would like everyone to kind of have an understanding, just like we did with the regression methods and all of that. I would like everyone to have an understanding of what all of these are. You can do them with pandas, you can do them with sklearn, right? So this is kind of the summary in feature engineering. When we come in next week, we will touch a little bit on feature engineering as the first part of what we want to do in how we can prepare our data and pipelines using sklearn pipelines to just fit the feature engineering into the model training. So that's all on feature engineering. Are there any questions? Okay. So I have a question. What's the difference between data wrangling and feature engineering? So data wrangling is basically the first part of feature engineering. Data wrangling is where you are cleaning the data effectively, cleaning it and um, transforming it, right? Um, so you are just working with data. Feature engineering is where you do additional transformation, right? Encoding and creation, adding of new features. So it does seem like they are not that different, but data wrangling kind of stops with where you say, okay, all the mail, M and so on, I kind of stand what's the word now? I I clean up the categories, right? I don't want to say normalization and standardization, but that's kind of what you're doing, right? I convert dates, to standardized date format, right? Um, Categories, right? All of that. So data wrangling ends up with cleaning the data, removing empty values or no values, removing duplicates, and all of that. That's really where it ends. Feature engineering starts kind of from there. But then data wrangling is actually a part of feature engineering. But feature engineering will go ahead to do things like adding new features, adding new features based on kind of, let's say, polynomial boosting with polynomial values, um, you know, adding multiplication ratios, all of those things that we talked about. Then encoding categorical values, so the one-hot encoding, the label encoding, embedding, text, right? Using Word2Vec, Glove, and all the rest of them, or even other models to embed. So that is now the additional stuff that feature engineering does. So the short answer is data wrangling is a subset, is part of feature engineering. You have to do data wrangling as part of feature engineering. Then gradient boosting and XGBoost. This is gradient boosting um is used for random forests, right? And decision trees. And basically it's just a way of um boosting the gradients. It's kind of an extension of gradient descent, right? So um typically you would combine multiple weak models, right? Multiple weak decision trees in a kind of sequential iterative process, right? So it's like you take one decision tree, you chain it into the next decision tree. And so each of the new models or decision trees in that chain, you train it to correct the errors made by the previous tree, right? So at the end of the day, it will, if you chain like 2, 3, 4, it will kind of improve the overall accuracy, right, of the entire model, right? Um, that's because, well, typically, a decision tree like we said, may have biases, it may overfit, right? So, but when you chain it, just like with the random forest, where we run them in parallel, we run multiple trees in parallel, and then we combine the prediction. The combined prediction of a random forest comes from the individual predictions of each decision tree, right? In the same way, in this case, you are not um running them in parallel, you are chaining them sequentially, and then you are training it that way. Okay. So at the end of the day, you have an output that is better than if you're using just one tree. So XGBoost is a method or a class or a tool or an algorithm, right? In in sklearn, right? That allows you to do extreme gradient boosting, if I may put it that way, right? So XGBoost is just a library that allows you to do um, gradient boosting, and it's really good at it. We didn't have the chance to do XGBoost when we were talking about decision trees and random forest last week, but I will look for either an opportunity to do that, or maybe I'll share a Jupyter notebook where where we can where I've done that, and we can share it. So that is it. Are there any other questions?